So reminder, what does it mean for the data to be normally distributed? Going back a couple slides here. The data is normally distributed if we have a symmetric bell shape in the graph of the histogram. If 68% of the data is within one standard deviation of the mean, right? So that would be this group here. We look one standard deviation on each side and we count. If 95% of the data is within two standard deviations, so we collect all of the data, that's this far to the left and this far to the right of the mean, and we count them up, that comes out to 95%. And 99.7% of the data is within three standard deviations. Now, it's not safe to assume that any data set you look at is going to be normally distributed. So if you looked at all the test scores at a particular school, they are extremely unlikely to be normally distributed. Ain't going to happen. If you looked at the heights of all adult males in the United States, I bet those are normally distributed. But if you looked in a specific town or a specific school, they're probably not. Okay? So the normal distribution is super powerful and an important part of statistics and predictions with statistics, but it has a history of being misused and abused. So we do have to be careful with its application, but you will come across it when you're looking at data about student achievement. It's going to come up. Percentiles in particular are going to come up. Sometimes z-scores are going to come up, but this expectation about that middle 68% is going to come up often. And it's just something you need to be aware of. So let's just look at a couple more examples. And what I'm looking at here is trying to get used to those 68, 95, 99.7 percentages. So I have a normal distribution. If I have a normal distribution and I look at a graph of the data, I should expect to see this symmetric bell shape. I should expect to see that in the middle, the mean and the median pretty much line up. There's always going to be a little bit of weirdness in the data, but they should be pretty close to the same. And then this time, instead of looking one, I'm going to look two standard deviations on each side. So this would be whatever the mean is plus one standard deviation, and this number could be whatever the mean is plus two standard deviations. This number here would be the mean minus a standard deviation. This would be the mean plus, minus two standard deviations. And those ideas of counting by standard deviations are z-scores. So in the middle is z equals 0. That's one standard deviation to the right, two standard deviations to the right, one standard deviation to the left, two standard deviations to the left. And then I look at the data. We'll do this in a spreadsheet in a minute. And then I count up all of the numbers, all of the data that starts here and ends there. And I want to know what is in, how much of the data is in that region right there. And what we should see is that about 95% of the data should be in there if we really have a normal distribution. All right, so let's see. If 95% is in the middle, then the tails have 100% minus that 95% to share, which gives them 5% to deal with. So then in this upper tail right here should be half of that 5%, or about 2.5% of the population should have values this far and higher. And on the other side, if I look at whatever that number is, a z-score of -2 and lower, I should expect, again, about 2.5% of the data. So if somebody has a score that's 2 standard deviations above, okay, what do I know about it? Well, they're 2 standard deviations above average. sorry, my pen is not tracking well. Deviations, there we go. Of average. Now I also know that they are at the edge of that middle 95%, and there's that additional 2.5% below that. So 95 plus 2.5 means that 97.5%, actually I don't want to word it that way, that score is higher, state it like I did earlier, than 97.5% of all of the others. Anytime I make a mark and I say, hey, there's a certain percent that's below that, that's the idea of a percentile. So this would be the 97.5th percentile, P 97.5. And a percentile just marks the place where a certain percent is at or below that point. So that's a percentile. And if the data is normally distributed, then we should see that about 97.5% is below that. 2.5% of the people did better, had a higher score, if we're talking about scores. But it could be something else. So let's do an example with a data set. And I had a data set of birth weights that I thought was worth looking at. And if you want to try this with me, I will share this link. Anyone with the link can find and view. Yep, that's what I want. So if you check the chat, or in the future, look in the description of the YouTube video, there should be a link to this file here. So what I want to do is I want to get a histogram of it, see what it looks like. Does it look like it has a symmetric bell shape? And then I want to test out with the standard deviation and the mean, does this data meet that rule? So let's play with this. And then this must have been a different class I was playing with. I took a sample of 100 of those weights in this other one. So we're not going to do that sample. We're just going to work with the birth weights here. And let's see, this one is in view only mode, protected. So if we want to work with it, we got to make a copy. So make a copy of it. And let's give it a better title. Birth weights 2020. So if you want to do the same kind of play, you can make a copy of that file. It'll be different than the file I have here in front of me right now. All right, so I want to get some summary statistics on here. And the main things I want to get for this is I want to know what's the count, what's the sample size. Sample size, what's the mean, and what's the standard deviation. So count is just count, and then counts numbers only, says I have 1,115 birth weights, and these were collected from a hospital in Philadelphia in 1990. Mean is average, and I think the only thing I have in that column is the data. I'll verify that in a second. So we should only click on the letter at the top of the column and select the whole column if we're sure the only thing in the column are numbers and a title. If there's anything else, any other numbers that aren't part of my data set, that's going to mess things up. So I think it will confirm that I'm not messing things up here. Oops. Calculating the average with only the data. Of quick way to get all the data, click at the top, and then Control-Shift-Down arrow will look for the end of the list. Exactly the same number. I did. Okay, so that means the only thing in this column is the birth weights, and these are in grams, and then the heading at the top. Standard deviation is usually stdev.s, because mainly we work with samples, rarely do we have the whole population. And then data. Okay, so we have and then let's round it. So these are all whole number grams. General rule in statistics is to round one more decimal place than the data had, so I would round these to the nearest tenth. So let's clean that up. And if I go too fast on something and you're live with me here, be sure to ask me to slow down, or what am I doing? So this should be the center of the distribution. If it's symmetric bell shape, or symmetric in general, then the median should be the same. So if I just double check the median here before I graph it, just for fun. Data. The median, the mean is a little smaller. Does anybody remember from last class what that means about the skew if the mean is less than the median? Does that mean skewed left or skewed right?
Does it skew right?
Yeah, so it turns out the tail pulls the mean away from the median. So if the mean is smaller, then there's some lower numbers pulling the mean away from the median's version of the center. So my mean here is less than the median. So what I expect to see in the graph then is I expect to see a skew left. And sometimes it's not always that straightforward. And I have a rough idea about what this data set does. So let's make a graph and check it out, and then we'll check the mean, standard deviation, and those empirical percentages. So to graph this, I can just do the column heading, the A at the top, chart, and we're not going to make a frequency table here, we're just going to make a frequency histogram. All right, so Google made this histogram here, and definitely a left table here. Now Google picked some numbers, let's see, 151, 303, 454. I might clean those up a little bit. So to clean up the numbers, customize histogram, and then instead of auto, if we like the number of columns here, we could just go with about 150, is about what Google picked there. So then my numbers are a little cleaner, 150, 300, 450, 600. This has a lot of columns. Looks like almost 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, more like 30 columns. Usually we aim between 6 and 20 columns. So maybe that's too many. So maybe I could try a bucket size of 200 or 300. 200, that's still a lot. There's no best histogram, remember, there's just different histograms. 300. I think I'm actually going to use 500 because it's a nice number. That's not too few. Now let's go with 500. I like that one. And again, there's no best histogram. There's just different histograms. So you pick something that you like for whatever reason. Maybe it's the ease of the numbers at the bottom. Maybe you just think that one's cuter than the rest. So that's the one we're going to go with. So what I'm going to do is I'm going to bring this into my drawing program, and I'm going to mark off the mean and the standard deviation on here. So I'll show you how to do that. We did that last week a bit. So I need a screenshot, and I guess I need a better title before I do that. So let me improve this graph a bit. Edit, customize, titles. So this would be birth weights in grams. Weights, weight in grams, and then it's usually good to have a vertical. It would be number. Title. Okay, I think that's better. Oh, now I'm going to screenshot it. Okay, and then my mean. Let's say it's about 3,200. And again, that's grams. So if I round that, I call this about 630, 600. Maybe I'll just call that about 600. No, I better be a little bit more careful about that. Let's see, I know what we'll do. We will make some calculations in the spreadsheet rather than just eyeball them. So I want to know about standard deviations. So maybe I'm going to make a column for z-scores. And the z-scores I want are -3, -2, -1, 0, 1, 2, and 3. And looking at this, there's definitely this tail over here, so it's not quite symmetric, but if I made a cutoff, say around 1,500 or 2,000, the rest of the graph has a relatively symmetric bell shape. So some of the graph is a symmetric bell shape, but there is a bit of a skew. So I don't quite meet the first condition of being a normal distribution. I have some premature births here, but notice there's no unusually large births. So one might wonder, how come there's some premature, some very small birth sizes, but there's not very many large birth sizes above average? That's an interesting question. And then here we're going to actually calculate the birth weights that go with each of these z-scores. Remember, 0 z-score is the mean. So next to the 0 here, I'm just going to go equals and click on the mean. So that number goes in the middle there. Do not want to fill these, Google. And then underneath here, that would be a z-score of 1 means 1 standard deviation above the mean. So then go equals, what is the mean, plus 1 standard deviation. On the other side, I think I'll highlight this, that's my middle. On the other side, -1 z-score means from the mean, subtract a standard deviation. So equals the mean minus a standard deviation. So a birth weight of about 3,800 grams is about 1 standard deviation above average. A birth weight of about 2,600 grams is about 1 standard deviation below average. Let's get some other ones. So a z-score of 2 means from the mean, go up 2 standard deviations. So equals the mean plus 2 standard deviations. So plus 2 times that number. And keep going. So we're going to get each of these here, the mean plus 3 standard deviations, and you have to use the asterisk to multiply, otherwise the spreadsheet will not cooperate. On the other side, -2 z-score means from the mean, take away 2 standard deviations. From the mean, take away 3 standard deviations. And if you wanted to do this too and you're having any trouble with it, I will reshare this. So this is a different version. I have to make sure it is shareable. Anyone with the link can view. So remember, when you share a Google Doc, double check that. I'll put that in the chat. So here's the new birth weight sheet. So if you had any trouble making those calculations happen and you wanted to see my formulas, how I use that, got them there. Okay, so I want now to mark these numbers on my graph to just kind of get a visual of what's going on. And then I want to try to do some counting here in my list. So I'll show you how I do those two things. So first I need to see these numbers and I need to see the graph. So having it sketched digitally on paper is helpful. So I'm going to head over to my digital board here for a sec, and then I'll come back. Current page. All right, so here are my values of weights that go with each of the standard z-scores there. So the mean is about 3,200. So that's 3,000, 3,500. So 3,200, I think, would be about right here. So that's the mean. So that would be the z equals 0 for z-scores. One z-score above is 38.5. So let's see, that's 35. That's 4,000. Right in the middle is 37.5. So 38.5 is probably about here-ish. So that would be one above. Two above is 4,486, almost 4,500. So it's just a little bit below that edge there. So maybe right about here is 2. And what we should find is these are equidistant, here to here, here to here, because we're counting by standard deviation here. Going the other way, and again, I could go one above, so if this is 4,000, 4,500, the end here should be 5,000. So the third standard deviation is just outside of my data here. And these red numbers are the z-scores. The gray numbers are my weights. One below 2,586. So 2,500, 3,000, probably about here-ish would be a z-score of -1. -2, 1,952-ish. So 15, 17.5, and pretty close to 2,000. Let's say it's about right there. So that'd be a z-score of -2. And let's see, -3 would be 1,319-ish. So 1,000. 1,500 in the middle is 1,250. So maybe just right about there-ish would be 3 standard deviations below. And what we'll check is, let's check the 95%. What we should find is if we count all of the birth weights from here to here, that represents 95%, oops, not 99, 95% of all of the birth weights I have. So all of these, count all of those up. So we're going to sort the spreadsheet and try to count all of these. And there is an easy way to do it and a harder way to do it that's more accurate. We're going to do it the easy way. Let's see if that's true. And again, that's a question mark. I don't know if it's true. Right? Is this perfectly symmetric? The answer is no. Does it have some symmetry about the mean? A little bit if we ignore this tail over here. That's a little, makes it skewed. So here I want to count, so I'm going to highlight this group. I think I'll highlight in green there. And then I'll make my mean bold again. So anyone with a birth weight of just above or just at or above 1,952 up to a birth weight of 4,486. So we're just going to sort the list and look. So to do that, I need to highlight my list. And then if I want to leave the title at the top, then I got to go to data, choose this 5th option, sort range, say it's got a header row. I can leave that name at the top. And we can go from smallest to largest, sure. All right, so that sorts them. So we want to make a mark. Where's the first number that's just above 1,952? So I guess 2,000 is the first one above 1,952. So I'm going to highlight that one in green. And I want to count all the way up to the number just below 4,486.6, so 4,486. There's over 1,000 birth weights here. So it's way down here, 486. Okay. 4489, 4480. Okay, so that's the end of my counting right there. So let's make that one green also. So then I'm just going to highlight with my mouse that number down to the other one I marked. There is a way to tell the computer to count if it's greater than some number or less than the other, but it's kind of a pain in the butt to write that formula. So I'm not going to go over that right now. If you really want to know about it, I can show you later. It's not all that exciting. Oh, too far. And on a spreadsheet, when you highlight a bunch of numbers in the bottom right, they throw a summary statistic at you. They said, hey, we can add all those up for you, but I don't want them added up. I want the count. And so there's count. So from my first number to my last number I highlighted, I count 1,061 numbers in that range. So I'm just going to go back up here and make a note of that. Let's move this out of the way. So I'm going to put that here. So then 2 standard deviations, I counted 1,061 numbers. Now there's a total of 1,015. So now I want to know, okay, what's this divided by 1,000? What percent is that of the total? Right. So this is just the count. I want to know what is it as a percent. So that means I'm just going to take my count and divide by the total to get a proportion. And then turn it into a percent. And hey, it looks like it's pretty close to 95%. So in order to check to see if something's relatively normal, we got to check basically 4 things is what we look at. 1, when you look at the graph, does it have a relatively symmetric bell-shaped? And a lot of people would say, nah, that tail, that's just too much. It's not. But this part here is relatively bell-shaped. So I ignored the tail and I moved on. Within 2 standard deviations, I do meet the empirical rule. Empirical rule says you should have about 95% within 2. If we made the same count within 3, let's try that one for fun. 3 STDs, standard deviations. So that would be from anything just above 1319 right up to 5,120. Now that was beyond my biggest number when we were looking at the histogram. So basically everything above 1319. So 1319. Yeah, we have a big jump from 1250 to 1421. So from 1421, I just Control Shift down arrow takes me to the end of the list. And yes, here's my max, which is definitely less than 5,000. And Google says I counted 1,094 numbers. So let's see how that works here. Back up to the top. Easier to grab the scroll bar. And 1,094. So I count within 3 standard deviations, 1,094 of the birth weights. If I divide that by the total number of birth weights, what do I get? 98%. And usually we get like 99.7. So I'm a little shy of that one right there, that statistic. So empirical rule says you should get 99.7%. I got 98%. I'm a little off. Why am I off? It's skewed left, that's why. So this isn't quite normally distributed, but the percentages are similar because it's skewed, but not too bad. And I imagine that the count for 1 standard deviation is going to be a little off. So I'm going to find that too. What if we go within 1 standard deviation? So that would be from 2,586 up to 3,853. So let's see, 2,586. 2,585, 2,587, so 2,585. Okay, so the next one after 2,586 is this one. So maybe I'll make that one red. And then how far do I want to go again? Up to 3,853. All right, let's look. Here, 3,853. Slowly getting there. 3,853. 3853, where are you? Getting close. 3853, that's as far as I can go right there. All right, what do we got? 828 numbers in that range. And I'll highlight that one for a reminder. Oh, no, I forgot what the number is. Darn it. Okay, no problem. Control Shift up arrow and then look down for that red number. It's there. There it is. 828. Okay. 828. Don't forget. You guys can remind me. How much was it? 828. How close is that going to be to 68% of the data within one standard deviation? Let's see. 74%. Okay, so what explains it being different? The skew. And again, there are symmetric distributions that don't meet the empirical rule. So I had a couple of points here. One, just because the normal distribution is popular and in a lot of research doesn't mean we find it everywhere, but it is related to pretty much almost all statistical predictions. And there's a big reason for that. You're going to take a couple of statistics courses to get why. I'm not going to get into it here. It's a little bit complicated. But the idea of grouping, counting by standard deviation, this idea of a z-score, these percentiles that we're working with, I'm mostly doing that to just give you more experience with those ideas. And what is a percentile? A percentile is just a position you mark to count what percent is below that point. Here, I'm not working with percentiles, but I'm working with middle 74% is what I have here. Right? So that's middle 74%. What's this 95%? That's the middle 95% of the data. Why is it middle? Because I'm counting standard deviations, and you can only count standard deviations from the mean. This number right here is my mean. Right? So the biggest reason I'm doing this stuff is to just try and get you used to the idea of mean and standard deviation. They work together. You can't have a standard deviation without a mean. Okay, so let's look at another problem related to this.